This diagram shows the complete cosmic inventory of our universe. Every star, planet, and atom we have ever detected accounts for just 5% of the total. The remaining 95% consists of two invisible placeholders, 23% dark matter and 72%. Decades later, Vera Rubin identified the same anomaly in the rotation of individual spiral galaxies. Her data was so precise that it forced researchers to accept the existence of an invisible mass, dark matter, which provides the extra gravitational pull needed to hold these structures together. We now understand that the visible universe is suspended within a massive, invisible structural web. We can measure its effects on the movement of galaxies, yet its actual nature remains a mystery. For decades, the consensus was that the gravitational pull of all this matter should be slowing the expansion of the universe over time. This graph compares our expectations with reality. The dotted line shows the predicted deceleration, but data from exploding stars in the late 90s revealed the solid line. The expansion of the universe is actually accelerating. To account for this outward push, physicists introduced a second variable, dark energy. While dark matter acts as the glue pulling things together, dark energy acts as a force field driving space itself apart. Dark matter and dark energy are the dominant forces in our universe, yet they exist entirely outside our direct observation. One leading theory is that dark matter consists of WIMPs, weakly interacting massive particles. These particles would exert gravity, but ignore the electromagnetic force, meaning they could pass directly through solid objects without any interaction. Dark energy is often explained as vacuum energy, a force generated by virtual particles that momentarily appear and disappear throughout empty space, creating an expanding pressure. To find these particles, we have built the largest machines in history. At the Large Hadron Collider, physicists smash particles together at nearly the speed of light, hoping to detect a signature of these dark substances in the debris. Other experiments take place deep underground, like the Gran Sasso laboratory in Italy. Researchers use supercooled crystals buried under a mountain to block out interference, waiting for a single dark matter particle to strike a sensor. Despite decades of searching with these sensitive instruments, we have not achieved a single direct detection of a dark matter or dark energy particle. The lack of results has led some researchers to ask a different question. What if we haven't found these particles because they aren't there to be found? Our current map of the universe is built on the laws of gravity established by Isaac Newton and Albert Einstein. We assume these rules for how mass curves space apply equally to a falling apple and a rotating galaxy. Some physicists argue that our detectors are simply not sensitive enough yet, or that the particles are more elusive than we imagined. Others suggest the issue may be with the underlying gravity models themselves. This is the basis for MOND, or Modified Newtonian Dynamics. It proposes that at the very low accelerations found at the edges of galaxies, the laws of gravity change, removing the need for invisible dark matter entirely. The persistent silence from our particle detectors forces us to choose between two possibilities. Either the dark universe is made of particles we cannot yet see, or our descriptions of gravity are incomplete. The Euclid Space Telescope was designed to address this conflict by mapping the positions and shapes of billions of galaxies across 1/3 of the sky. Euclid's primary tool is gravitational lensing, a phenomenon where gravity acts like a lens to reveal the invisible. This diagram shows the process. As light from a distant galaxy passes a massive foreground object, the object's gravity bends the light's path. By measuring these distortions, Euclid can calculate exactly how much mass, both visible and dark, is present. By creating a digital twin of the real universe based on these billions of measurements, Euclid will show us how dark matter and energy have influenced the growth of cosmic structures over the last 10 billion years. Euclid is now providing a dataset of unprecedented scale, allowing us to test our most fundamental theories about the composition of the universe. The map could provide the first definitive evidence of how dark matter and energy are distributed, reinforcing the standard model and guiding the search for specific particles. However, if the distribution of mass recorded by Euclid deviates from our predictions, it will provide the evidence needed to refine or replace our current theories of gravity. The results will clarify the nature of the 95